Today we are going to talk about rotational dynamics. In this chapter, we are going to be more familiar with rotational motion and the things affecting it. Now, what is a rotational motion? Look here. This is a solid. It can rotate around a certain axis called the axis of rotation. This axis is horizontal and passing through the solid like this. So the solid is in rotation around one fixed axis called the axis of rotation. So which forces are capable of rotating the solid? Look here. This force is able to rotate the solid. Another force. Here. It also can rotate the solid. A third force, like this, can also rotate the solid around the axis of rotation. Now I will apply another force, like this. Let's repeat. Like this. Is it able to rotate the body? No. Another force, like this. This force is unable to rotate the solid. Another force, like this, is also unable to rotate the solid. Notice how this force was parallel to the axis of rotation. All forces that are parallel to the axis of rotation are unable to rotate the solid. This force, its line of action passes through the axis of rotation. All forces whose lines of action pass through the axis of rotation are also unable to rotate the solid. Thus, all forces whose lines of action are parallel or pass through the axis of rotation are unable to rotate the solid. Therefore, all forces that are able to rotate or influence the rotation of a solid are said to possess a moment with respect to a certain axis of rotation. This is a figure illustrating the solid, a rod with two identical masses, as shown. The force F that has this direction can rotate the solid around the axis of rotation. Another force F, like this, can also rotate the solid. These two forces can rotate the solid because their lines of action are neither parallel to the axis of rotation nor do they pass through it. We say that F possesses a moment with respect to the axis of rotation, where we write its symbol like this. So what does this quantity depend on? The rod is in equilibrium. As you can see. So we are going to remove one of the masses and place it farther away from the axis of rotation. So as you can see, the rod is no longer in equilibrium now. So why is that? So Earth attracts the first mass of 80 grams by a force called the weight of magnitude 0.8 newtons. Similarly, Earth attracts the second mass by a force of 0.8 newtons as well. But this force has a greater rotational effect than the one of the closer mass. Why? Because the weight of the farther mass is applied at a greater distance from the axis of rotation. The moment of a force depends on the distance between the point of application of the force and the axis of rotation. Here we have achieved equilibrium of the solid in this position. The 60-gram mass is at a distance of 10 centimeters from the axis of rotation, whereas the mass of 40 grams is at 15 centimeters from the axis of rotation. On the figure, the 60-gram mass corresponds to weight F1 of magnitude m times g equals to 0.6 newtons. And the other mass corresponds to a weight F2 of magnitude 0.4 newtons. The 10 centimeters represents the distance between the axis of rotation and F1. And here's the distance. We will call this distance OA. OB is the distance between the axis of rotation and F2. Let's find the answer to the product F1 times OA. It is equal to 0.6 times 0.1, and it is 0.06 Newton meter. F2 times OB is equal to 0.4 times 0.15, which is also equal to 0.06 Newton meter. From observation and by calculation, the rotational effect of F2 equates that of F1. Then it is not only the distance alone that plays role in equilibrium of the body, nor it is only the force. But actually it is the product of the force by the distance. The small force by the big distance balances out the effect of the big force by the small distance. F1 times OA equals to F2 times OB. So in order to achieve equilibrium, the quantities F1 times OA and F2 times OB must be equal. Let's take another example. The 80-gram mass is at 10 centimeters from the axis of rotation, whereas the 40-gram mass is at 20 centimeters from the axis of rotation. The 40-gram mass, which is farther away from the axis of rotation, is able to balance out the 80-gram mass, which is closer to the axis of rotation at 10 centimeters. In fact, this force, F1, is equivalent to 0.8 newtons by m times g, and F2 is equivalent to 0.4 newtons. So let's call the points A and B, respectively. F1 times OA equals to F2 times OB. Thus, the force and its distance from the axis of rotation are of great importance in rotation, or the moment of the force, which is expressed as moment of the force with respect to the axis delta, is equal to F times D. D, which is the distance between the force and the axis of rotation. Let's explain how to find the expression of the moment of the force. This is the distance between F and the axis of rotation. We're going to draw it. And this is the distance between F prime and the axis delta. The moment of F prime is equal to F prime times D prime, where D prime represents the distance between F prime and the axis of rotation delta. So what is the SI unit of the moment? The force is expressed in newtons, and the distance is expressed in meters. Thus, the moment is expressed in Newton meter. Let's choose a positive direction like this, for example. F will have a rotational effect on the solid in the positive direction. So we put a plus sign in the expression of its moment. F prime also has a rotational effect on the solid in the positive direction. So we also put a plus sign in its expression. But if we apply a force like this, for example, and let's call it F double prime, this force will have a rotational effect not in the positive direction, but in this direction. So it will have in its expression a negative sign. Hence, the moment of F double prime with respect to delta is equal to negative F double prime times D double prime. And here's the distance D double prime. Now let's demonstrate the rotational effect of F double prime. Notice how the solid turns in the negative direction. And if we apply force, a different force in this direction, the solid rotates in the positive direction. Similarly, F prime rotates the solid in the positive direction. The following application is to facilitate things. Now we have four different forces, F1, F2, F3, and F4. And the axis of rotation delta passes through O. The objective here is to calculate the moment of each force with respect to the axis of rotation. The moment of F1 with respect to delta is equal to F1 times the distance between F1 and delta. F1 has a magnitude of 4 newtons, and the distance between F1 and delta is the distance between O and the prolongation of F1. This distance is between the axis of rotation, and the prolongation of F1 is OA. So the formula becomes F1 times OA, and OA equals to 20 centimeters. But pay attention, Is it a positive or negative sign in the formula? To answer such question, we have to go back to the figure. Here's the axis of rotation. Where F is applied, it is in the downward direction. The rod rotates in the anticlockwise direction, which is the positive direction in our case. So the moment of F1 is now 4 times 0.2, which is 0.8 Newton meter. Now the moment of F2 with respect to delta, which is equal to the magnitude of F2 times the distance between F2 and delta, and we have to find this distance. To find this distance, we have to draw the perpendicular from O to the line of action of F2. Let's call this point D. So the distance to find is OD, where OD represents the distance between the axis of rotation and the line of action of the force F2. So the formula becomes F2 times OD. What is the sign of the moment? Here's the axis of rotation. The rod is being pulled by F2, so it rotates in the clockwise direction, which is the negative direction. So the moment of F2 with respect to delta is negative and is equal to negative 2 times 0.3, which is negative 0.6 Newton meter. Now, the moment of F3 with respect to delta is equal to F3 times the distance between F3 and delta. Going back to the figure, this distance between the axis of rotation and the line of action of the force is here. So we draw the perpendicular, and let's call this point H. Hence, the distance between the axis of rotation and the force F3 is distance OH. So we write F3 times OH. Is this quantity negative or positive? F3 is applied obliquely upwards to the left. So the rod rotates in the anticlockwise direction, which is the positive direction of rotation. And we put a positive sign in the formula. Now, how to determine OH? We consider triangle OHB. OH is opposite to the angle 40 degrees. So we write sine 40 is equal to the opposite side, which is OH, divided by the hypotenuse, which is OB. Thus, OH equals to OB sine 40, which is equal to 0.257 meters. And as a result, the moment of F3 with respect to delta is equal to positive 6 times 0.257, which is 1.542 Newton meter. Now let's find the moment of F4 with respect to delta, which is equal to F4 times the perpendicular distance between F4 and delta. Let's call this point h prime. So the distance to find now is OH prime. Is the sign of the formula negative or positive? As you can see, F4 rotates the rod in this direction, which is the clockwise direction, and hence we put a negative sign. To determine OH prime, we consider the triangle OHC, OH prime C. OH prime is opposite to the angle 30 degrees. So sine 30 degrees equals to OH prime over OC. Thus, OH prime equals to OC sine 30, which is equal to 0.15 times 1/2, which is equal to 0.075 meters. So negative 12 times 0.075 is equal to negative 0.9 Newton meters. And this is how to determine the moment of a force with respect to an axis of rotation. Let's apply another force, F5, like this for example. Let's give it a value of 10 newtons at a point we will call E. And given that the distance OE equals to 10 centimeters. This force makes an angle of 30 degrees with the rod. To determine its moment with respect to the axis delta, we write moment of F5 with respect to delta is equal to F5 times the distance between F5 and delta. To determine this distance, we have to extend F5 and to draw the perpendicular from O to the prolongation, such that this is OI, for example. Now OI represents the distance between F5 and the axis of rotation. This angle is also 30 degrees, being vertically opposite to the other 30 degrees. Now in triangle OEI, the formula becomes F5 times OE sine 30. And let's see how does F5 rotate the solid. As you can see, it can rotate it in the positive direction. And as a result, the moment of F5 with respect to delta is equal to 10 times 0.1 times half, which is equal to 0.5 Newton meter.